Well, hello, calculus children. Hope you are well. Man, today this is what is today? Friday. Friday. What an amazing hot day it was today. I actually was out chainsawing for a while and it was like ridiculously hot. Anyway, I am out in my Muskoka room recording, so it might sound a little bit different. Instead of hearing the grandfather clock in the background, you might hear the sounds of the birds and the squirrels and probably the muffled sound of my grandfather clock in the background still. Anyway, hope you're all well. So today we're going to talk about projections of vectors, and again, I've been trying to be as judicious as I can with what topics we need to cover, and projections is used in enough other places that if we don't actually talk about it, we're going to have a hard time kind of seeing where we're at with this. And I'm just thinking, should I be in? Now we're good with this. I was wondering if I had to be in Smart Notebook, but I like writing in this better. Okay, so projections. I'm going to write here. That's meant to be an asterisk. You can tell, I'm sure. Think of shadows. So that's just my little hint right now. So think of shadows. Okay, so if we take two vectors, let's get this color vector. Don't know what color that is. Blue, probably. I like blue. And we draw a vector. So what did I do? I did the wrong thing. Whatever I did, it's wrong. Oh, I hit the wrong button. Okay, sorry. So now this color. All right, red or brown or whatever it is. So we have one vector like that, and then I'm going to get my other one because I still like blue, and another vector like this. And what I want you to consider is I'm going to call this one here vector A, and I'm going to call this one down here, but you can guess, vector B. And I want to project, and I put this in quotes. I don't really know why I'm saying in quotes, because this is what we're doing. We're going to project A onto, and that's really important, A onto B. And the order we do this in is really relevant. A onto B is actually different than B onto A, so be careful. So we're going to do A onto B. So here's why I say think about shadows. So imagine that we took I don't think is that yellow? Maybe that's yellow. I don't know. That's yellow. I don't know. So we're going to take a light bar, right? So here's my light bar, and I'm going to place my light bar parallel to what I'm projecting onto. So I'm projecting onto B, so the light bar is going to be parallel to what I'm projecting onto. Okay, so this thing is, shining the light, as you can tell from the color that I chose. It's a bright color. And so it's shining a light down onto B. And then as you can imagine, what we're going to get is there is going to be shadow from A onto B. Okay, so A projects a shadow onto B. And so this spot right here, that is the projection of A onto B. Okay, and so if we think about this a little bit, we'll get to it in a second. So that's a projection of A onto B. Now, maybe I should have done this in Smart Notebook, but whatever. I'm going to redraw this, and then we're going to look at something else. So, that's not blue. Dang it, I want blue. There. Like that. So there's my B. I think it's a little bit bigger than it was originally, but whatever. B. And then A, is that red or black? I can't even tell. So let's go up here, get that one, and we've got A. Okay, it's going to be right here. There's A. Now we're going to do, I'm going to separate them like this. So that was A onto B. This, we're going to now do B onto A. And again, the onto is important. So this is B onto A. So I'm going to take my light bar this time, and I'm going to have to make my light bar be parallel to A, because we always want to do it parallel to what we're shining onto. So here's my light shining, I guess I can do it that direction so it's more obvious, onto A. Now, here's what's going to happen And you may say, haha, you've screwed up, Galbraith. Well, here's what's neat. The fact that the shadow is actually longer than the vector we're projecting onto is really immaterial. Okay, so I want you to think about shadows just because it's an easy way to do it, although shadows isn't really accurate, of course, because these concepts extend beyond kind of the physical domains that we're concerned about. But there is the shadow. So, and so this is B onto A. Okay, and so I'm going to even write that note. Okay, the shadow, that should be in quotes because there really is no shadow. The shadow can be longer than the vector you are projecting onto. So that's important. Okay, but notice the onto is really important because the onto tells me which one it's going onto, so which one I have to do the shadow onto. And in a moment, we're going to solve this for for the actual numerical side of things, and the onto is going to come into play again. To calculate this, so to algebraically calculate. I don't know if I mentioned this before in a prior video, but we've had Baltimore Orioles at our bird feeder lately, which is highly exciting because they're orange. And, this guy here, I can see orange really well. So I love that. So that was exciting because I've never had them at our bird feeder before. Calculate. Did I spell it right? Pretty close anyway. All right, so to calculate. So I'm going to draw this again one more time. You don't have to draw it if you don't want to, but I'm going to. So I'm going to do A onto B. I'm not going to read with the colors this time. So we've got, here's vector A, and here's vector B, and we're going to again do A onto B. So there it is. There's my shadow. What I want to calculate is I want to calculate what the magnitude of this is. Now, so here's some math. So I'm going to do, there's a theta right there. So the shadow, because I put the light bar parallel to B, the shadow itself off of the tip is going to be at right angles to the vector B. So what we actually have here effectively, if I only consider the shadow and vector A and the part of vector B that's the shadow, we have a right triangle. So we can use some SOHCAHTOA. And so I'm going to say that the point where, let me grab a different color to make it more obvious, the point where this shadow ends up, like the literal point, like where it stops, like this point right here, I'm going to call N, and I'm going to call the beginning down here O. And so I'm going to say that this would be a vector then, right? This would be in theory, but I'm getting ahead of myself. So I'm going to say that this thing there is ON. And so if we think about this in terms of a triangle, right? If I redraw this triangle, that's bad. Whatever. Okay, you know what it is. This would be the magnitude of A, would be on the hypotenuse. We'd have my theta down here, and this would be the magnitude of ON. So if I wanted to know how long this piece was, if I knew what theta was, I could use, this is adjacent to the angle, and this is hypotenuse. So we know, according to SOHCAHTOA, that the cosine of theta is equal to adjacent over hypotenuse, right? And so in this particular case, we've got that the cosine of theta is equal to the adjacent. Well, the adjacent in this case, again, because cosine or SOHCAHTOA doesn't deal in vectors, it deals in magnitudes, right? So this is going to be a length. So this is going to be the magnitude of ON over the hypotenuse, which is actually the magnitude of A. What we're really interested in is the magnitude of ON. So let's do some rearranging. So I can say, well, then that means that the magnitude of ON is going to be equal to, if I multiply both sides, the magnitude of A times the cosine of theta. Now, this is getting relatively close to something that we already know. So if we consider, right, so let me give me some more space here. So if we recall or consider that A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of theta. That's pretty darn close, right? That is, only a magnitude of vector B away from the definition of A dotted with B. So what I could do here is if I divide this side with the magnitude of B, divide this side with the magnitude of B, those are going to go away. And we have then that the magnitude of A cos theta is equal to A dotted with B over the magnitude of B. And you're like, okay, well, look, this is pretty cool. Symmetry here says this A cos theta is the same as this A cos theta, which means that this expression must actually be the same as this expression. And so what we have just found is we know now that the magnitude of ON, which is the magnitude of the projection of A onto B, is equal to A dotted with B over the magnitude of B. And in fact, ladies, gentlemen, children of all ages, this is a definition. Okay, so what that is right there, this is the scalar projection of vector A onto vector B. Now, why the onto B is really kind of nice that we say it like that. I'm kind of writing off the angles here. It's on vector B, right? So A dotted with B onto vector B, and it's onto vector B. So for me, that provides a really easy way to remember this, okay? So if I wanted to then, so imagine that I wanted to do B onto A, the definition, for the magnitude, that's why it's called scalar, right? Because it's just a magnitude, it doesn't have a direction right now. So the magnitude of the normal vector that is the projection is going to be equal to, like, we could do B dotted with A over, and then because it's on to A, the magnitude of A. Now the reality is it doesn't matter whether I do A dotted with B or B dotted with A because dot product is commutative, right? But the onto tells us which vector resides on the bottom, or the magnitude. So this is a scalar projection. Scalar projection, so it is scalar because all we've found here, so all we have calculated is magnitude. Okay, so without direction, which it doesn't have, so without direction, this is not a vector. Okay, so there is our definition. That is the scalar projection of A onto B. That's our definition. If I was doing it in Smart Notebook, I'd use the rainbowy highlighter doodly, but it's a big deal, right? So this is one of our definitions, and it's a definition that I would encourage you. This is something certainly that you can memorize. I'll be honest, I think I've told you guys before, I have an atrocious memory and I have a tough time memorizing these things. I can derive this pretty darn quickly just using, some primary trig ratios from back in grade 10, I guess. You can figure this out on the fly. If you do a bunch of them, you're going to memorize it anyway. But, if you leave it for any length of time, it's nice to know how we go about deriving it. And I just showed that. Now, that's a scalar projection. Let's extend this, spice it up a notch. So what we're going to look at now is, that was a nice straight line, a vector projection. Okay, so a vector projection. And again, we're going to start with A onto B. Well, what's it take to be a vector? Well, a vector has to have a magnitude and a direction. If you consider what we've done already, we've kind of got half of that demon slain, because what we have, of course, is we have the magnitude already. So we know how to get the magnitude. We know how to solve for magnitude. The peepers are out. I love the peepers. I don't know if you guys can hear it in the background. Okay, so we know how to solve for magnitude. We know that, the magnitude of A onto B is equal to ON. The magnitude of ON is equal to A dotted with B over the magnitude of B, which is what we just had. And we're all down easy peasy. We've got that. So I got a magnitude. I need a direction. Well, if we consider our diagrams that we had earlier, the direction needs to obviously be, because it's on to be, collinear, parallel, the same frickin' direction as what vector B was. So it's a number. Like, it doesn't look like a number right there, but if we calculated it, it would be an integer, or not likely an integer, more likely a real number, but it's a magnitude right there. So if we could add that magnitude onto a vector, we'd be good to go. The vector needs to go in the same direction as vector B. So could I just take that and multiply vector B with it and we'd be good to go? Almost, but what would be the problem is if this was, say this had a magnitude of 10 and vector B had a magnitude of 4, if I said, okay, take 10 times vector B, all of a sudden our vector projection would have a magnitude of 40, which is what we don't want. So some of you are maybe thinking how we could resolve this. We could turn vector B into a, wait for it, unit vector. So if we take the unit vector that is in the same direction as vector B, then we would be good to go. So I'm going to write that out. So we want a unit vector, and recall, of course, unit vector is very specific. So it has a magnitude of 1, right? So we want a unit vector in the direction of vector B, okay? And then we can multiply the scalar magnitude. I guess I don't really need to say scalar magnitude, because if it's a scalar, it's a magnitude. Nevertheless, a scalar magnitude, multiply the scalar magnitude with the unit vector in the direction of B. Okay, well, so if I got this vector B and I want a unit vector in its own direction, we've talked about this. We might have forgotten. So vector B is just vector B. So I'm not going to say equals to. What I want is I want a unit vector in the direction of vector B, right? So a unit vector, its symbology has a hat. A unit vector in the direction of vector B is going to be, we take the vector B and we divide it by its own magnitude. Okay, so if we divide B by its own magnitude, it's in the proper direction, but now it's only 1 unit long. So if I want the vector projection of A onto B, okay, so if I want, so I'm going to maybe just, do a little note here. This is the unit vector in the direction of B. Okay, that's good. So if I want the vector projection of A onto B, here's what we're going to do. We're going to take this, right? So we have ON, and I'm going to come back and adjust this in a second. But this is the magnitude, right? So this is the proper magnitude. And then I want to multiply that with the B hat, right? The unit vector in the proper direction. So that's the magnitude, and this is the unit vector in the right direction. Vector in the correct direction. So what we can do then is we can say ON, where ON, notice, is not a magnitude anymore. It is the projection of A onto B. Maybe I'll say this is, we're going to call that ON just to make sure it's clear. we're going to do these things. So the magnitude of ON, we already have. We defined that earlier. It's A dotted with B over the magnitude of B. So we've got A dotted with B over the magnitude of B. So that's this is the same thing as this. That wasn't good. Whatever. And then we're going to, was that in black? I can't even tell. And then we're going to do the unit vector in the direction of B, which we know is vector B over the magnitude of vector B. Okay. And so what we have there is that this is the actual definition of the vector projection. So this is the vector projection of A onto vector B. Okay, so that is a definition. Now, there is a somewhat more simplistic way of writing that maybe at some future juncture we'll talk about. I prefer for you to think about it like that so that you understand the derivation and where it's come from. So yeah, so there we go. That's a thing of beauty. Lovely, 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 lovely. Okay, so nice, all good. So let's actually do some practice with some actual examples. So imagine that I said, I'm running out of space here. We're good. We can go. We're no problem. So I want to example. Given vector A is going to be equal to 3, 2, and -1, let's say, and vector B is going to be equal to 6, 4, and 1. Two things. First thing I want you to do is I want you to determine the scalar projection. Okay, so grab me the scalar projection. And number 2, of course, no surprise, I want the vector projection. Okay, so for number 1, this color, I like that. Number 1, we're going to do the scalar projection. Well, the scalar projection is the magnitude of ON is equal to A dotted with B. And because, I didn't even say which one I want to do. For both of these things, I want it to be A onto B, and similarly A onto B. All right, so the magnitude of ON is going to be equal to A dotted with B, and because it's onto B, I know the magnitude of B goes in the denominator, right? So A dotted with B, so we're going to need that. So A dotted with B, so let's calculate it. A dotted with B is going to be equal to 3 times 6. I have to be careful with the times now, right? Like the dot means something, but because it's just integers, we're good to go. So 3 times 6 plus 2 times 4 plus -1 times 1. So let's add those beasties up. So that's 18 plus 8 minus 1. So that is going to be, I guess, 25. Lovely. I can see that I'm going to need the magnitude of B. All right, the magnitude of B. Well, that is basically just the big application of Pythagorean theorem in the grand scheme. And so if we're going to do that, it's going to be the root of 6 squared plus 4 squared plus 1 squared. So that's going to be the root of 36 plus 16 plus 1, which is 53. So the root of 53. Lovely. So back here we come. And we're going to say that this is A dotted with B. So we said that that's 25 over the magnitude of B, which is the root of 53. Lovely, lovely, lovely. Okay. So that is the scalar projection of A onto B. Let's go vector projection. Go for a different color. Is there like a green? That's like green. Green? I think it's green. 2. So I want the full magnitude or the full vector. Well, it's going to be this, right? So that is the magnitude. So 25 over the root of 53. But then we have to multiply it with the unit vector in the same direction as B. So I really want B hat. Well, B hat is just B, right? Divided by the magnitude of B. Well, B is 641. Okay, so 641 and divided by, so or times 1 over the root of 53. So there's two ways we could write it. We could write it just like that, or we could distribute that into there. Either way would be good, but if you kind of examine what's going on over here, you probably realize that it's probably going to be nice to leave that as the, as a coefficient. So I'm going to come over here and I'm going to say, all right, this is going to be this times 1 over the root of 53 and times 641, which is equal to 25 53rds times 641. 1. And there it is. That's what it is. Yay, us. So that is the vector projection of A onto B, which is a good thing. Okay. We could write that alternatively, right? We could then say, I'm happy for you to write it like that, but contextually, sometimes it's handier to have it the other way. So I could distribute this into each of those pieces. And in that case, I guess it would be 150 53rds, if I've done that right, 100 53rds and 25 53rds. Okay, so I would totally be down with accepting either one of those two answers as your vector projection of A onto B. Okay, lovely, lovely, lovely. I think, because I don't think I've gone that long, although I have no idea, I'm going to do a little bit more. We're going to do some direction cosines. Now, I didn't make this quite big enough. So I'm going to save this, and where's it going to go? We're going to call it as a JPEG. So funny story, I was driving into town today to pick up more drywall compound for the kitchen reno stuff that we're doing, and I was driving along, and I kept on, I had a hair in my eye, and I kept on thinking, gosh, I get Brianna's hairs all over me, or my wife's hairs all over me, and I thought, I can't believe I got one of these hairs. And so I was trying to get it out of my eye, it was my own. I have never had hair so long in my life that it could actually get in my own eye. I was so confused and distracted. I'm going to have to get a haircut soon. What are we doing? This is projections. Projections. Okay, there we go. Yeah, looks lovely. And file new. It's getting dark out here. I'm going to have to turn the lights on. Okay, so we're also going to do, while we're at it, direction angles, sometimes also known as direction cosines. So direction angles or direction cosines. And you're going to find out why in a second it's called direction cosines. No worries. Okay, hang on a second. I'm going to turn my lights on. I can hardly see. There we go. Okay. Let's see. Imagine, let's say, given a vector. So given vector B is going to be equal to 1, 7, and 3. Oh, I've got the ceiling fan going. I don't really need that. Whatever. Okay, so I would like to know what, and I'm going to put this in brackets, acute angles does, that's not how you spell does, does vector B make with each axis, and so I mean the X and the Y and the Z axis for those of you that are directionally challenged. Okay, so I'm going to just draw this to kind of get us thinking about this a little bit. So I'm going to do myself up a 3D set of, oh, that's not a line, 3D axes here. There we go, right there. Close enough. Okay, so 1, 7, and 3. Let's do this in blue or whatever color this is. 1 out the x-axis, 7 a long ways out here, and 3 up here. Okay, so we're talking about the vector that goes like that. So there is vector B. Now, I want to know what angle, and it's hard, this is a 2D representation, but I want to know what angle does this make with each of the axes. So, what angle is going on in here? And, grab a different color. What angle is going on here? And then a different color yet again. What angle is going on in here? So those are all the angles that we are actually interested in. Now, there are conventions for the names of these particular angles. Normally, the x-axis is listed, the angle with the x-axis is listed as fishy, or alpha, if I could draw it better. Some beeping, whatever. It's not my house. And then with the y-axis, so this is alpha. You can maybe guess what we make with the y-axis. This is often called beta. And then the last one, I believe, is gamma. Okay, so it's like a fishy that's pointed downwards. Lovely. So these are what I want to figure out. So I want to know what angle does it make with each of these axes. So at first glance, it kind of maybe seems, somewhat complicated of what's going on here, but it's not. And so if we think about this axis right here, imagine, so I don't know what color I used there. I think that's maybe red. Imagine that I took this vector and I just made a vector. What was that one called again? I hopefully remember. That was the I. That's not an I hat vector. So there's my I hat vector. And what are the coordinates of the I hat vector? Well, remember, I hat is 1, 0, 0. So if I thought about what I hat dotted with B is equal to, what would that be? Well, I know the definition of A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between them. Interesting. So if I did I dotted with B, I know that's going to be the magnitude of I, we know what that is, times the magnitude of B times the cosine of the angle in between. Well, what is the magnitude of I? Well, the magnitude of I is, it's 1. And the magnitude of B, well, we can get that, right? The magnitude of B is equal to the root of 1 plus 49 plus 9. So it's equal to the root of 59. So we can come back here and we can say, this is the root of 59. And it's like, okay, that's, fewer variables to worry about, but lucky, I want to know what theta is. So cosine of theta. Can I calculate what I dotted with B is? Yeah, dead easy, right? I dotted with B, it's just 1, 0, 0 dotted with 1, 7, 3. And so the zeros are just going to squish the 7 and the 3 are going to be gone. It's just going to be 1 times the x. So in fact, this is just going to be the x coordinate is equal to that. Okay, and so then what we can do is we can say, if we consider this in alternate terms, or actually let's just finish this off. And this is the x coordinate. This is not a random x variable, x coordinate. So in this case, it's 1 is equal to, because that's the x coordinate, right? 1 times the root of 59, or equals root 59 cos theta. Divide both sides by the root of 59, divide by the root of 59. And what we're going to get then is the cosine of theta is equal to 1 over the root of 59. And so we could do the cos inverse of that. I don't really know what it is. And so that's going to be that the cosine of theta, or let's not do that. How about we say that means that theta is equal to the cos inverse of 1 over the root of 59. Okay, so that, or we shouldn't use theta. I guess I should have used my alpha here, whatever, you know what I mean. There we go. So, maybe I should grab my calculator and actually try and do that, see what it actually is. There it is. Boop-a-doop. mode, make sure that we're in degrees because we're talking degrees again just to make our lives easier. So we would do the cos inverse of 1 divided by the root of 59. And what do we get? We're going to get 82.52 degrees. So we found it. So theta equals 82.52 little degrees. So here's what we can do if we're going to consider this in general. So if I want to know the direction angle or the direction cosine, cosine right there. So the direction cosine with the x-axis. Let's look at it in general. We know that it's going to be the I hat vector dotted with whatever vector you're using. Let's say m, so the direction cosine of the x-axis of the m vector. It's going to be equal to, again, I'll write it out and we're going to simplify this, I hat magnitude times the magnitude of m times the cosine of the angle. Well, this is always going to simply be the 1, right? That's always going to be 1. And then the magnitude of m, I'm just going to leave, so I'm going to say 1 like that. And then the magnitude of m is just the magnitude of m times the cosine of theta. Now over on this side, what we're going to do, so maybe I'm going to say is equal to a, b, c, right? M, or the I hat dotted with m is just going to be the x coordinate. So in this case, it would be a. And so if we would then do some rearranging, we can say, oh, the cosine of theta is equal to a over the magnitude of m. Okay. And similarly for the other axes, right? So that's with the x-axis. If we want to do it with the y-axis for the same thing, it would be, the j hat vector dotted with vector m is equal to the magnitude of j hat times the magnitude of vector m times the cosine, and really I should have done alpha and beta, but whatever, you know what I'm talking about, which in this case is going to be j hat dotted with m is just going to be the b coordinate is equal to, and that's just going to be m, so the magnitude of m over the cosine of theta, divide both sides by the magnitude of m, divide by the magnitude of m, that's going to go away. And similarly here again, we're going to say, oh, that means that the cosine of theta is equal to b over the magnitude of m. And by, some extrapolation, we would know then for the z-axis, and you could derive that on your own if you really chose to, it's going to be the cosine of theta is equal to c over the magnitude of m. So those three things, maybe I should write them with the appropriate. So, the cosine of alpha is equal to a over the magnitude of m. The cosine of beta is equal to b over the magnitude of m, and the cosine of, I may have that wrong, gamma, I think is what it is going to be equal to c over the magnitude of m. And so this is for the x-axis, this is for the y-axis, and this is for the z-axis. Okay, so that's important. Although, you know what? I never ever memorize that, again, for the same reason that I can derive that awfully darn quickly. But that's just me, and I have a crap memory. All right, so here's some stuff for to practice. Page 399, numbers 6, 7, 11, 12, and 13. Okay, there we go. Hope everyone has had a shiny star of a day. Lovely.